Okay, everyone, let's look at some more problems. This one's a bit different. So what we have here is a 4-kilogram slender rod. Why are all these slender rods in these problems? I don't know. And it's initially supported horizontally by a spring at B and a pin at A. And we want to find the angular acceleration of the rod and the acceleration of the rod's mass center at the instant the 100 Newton force is applied. So at that exact instant when that 100 Newton force is applied. So your plan to solve this, because I'm going to send you off to try on your own, is to do the following. First, find the spring reaction force before the 100 newtons is applied, and then draw the free body diagram and kinetic diagrams of the rod. Then apply your equations of motion. So what's the reaction force going to be before it's applied, and then go from there. Because remember, this has a weight, and so it's going to be squishing down this spring to begin with. Okay, you try this, come back and tell me how you did. So 3, 2, 1, and you're back. I know you did amazingly, so let's try it out together. So first off, we need to figure out our reaction forces. So what we have here is we have a reaction force in the normal and tangential direction at point A. We have our weight pressing down. Sorry, that's not our weight, that's a force pressing down. And we have our weight right here. And we have a reaction force from the spring. And this is going to cause all of this together an acceleration of the centroid in the normal and tangential directions. Though the normal direction will be 0 because it can't move in that direction. And also, it's going to cause it to accelerate around the centroid. So first off, what is the spring force that is applied? What is the spring force that is applied? Well, an easy thing to realize is that before it's applied, there's 1.5 meters over here and 1.5 meters over here. It's evenly distributed. And so even though it didn't tell us how much this is compressed, we know it's going to be holding half the weight. If we do some forces in the X and some forces in the Y beforehand, we could solve for this reaction force right here. And the spring force would come to be 19.62 newtons. Okay, 19.62 newtons. So that's the amount of force that it's applying at that point. And so now we're going to apply our sum of moments around point A, because that's what it's rotating around. And so it's going to be equal to our mass moment of inertia times the angular acceleration. And so the moments caused by our spring force and the weight and that applied force are going to cause that angular acceleration around the mass moment of inertia. So we have our spring force right here. We have our applied force. We have the weight. That's causing that angular acceleration. So we plug in our equations for the mass moment of inertia for a slender rod. It's equal to the mass times its length squared over 12. Then we can solve and find out that the angular acceleration, just as this 100 Newton force is applied, is going to be 12.5 radians per second squared. And therefore we can plug in everything else because we already knew the normal component was going to be 0. And the tangential component is simply equal to the distance from where I am to the mass moment of inertia, to the centroid, and multiply that by the angular acceleration. So it's going to be accelerating downward at 18.8 meters per second squared. Okay, so that's it for this time. Thank you for listening, and I'll see you all next time as we do our last problem for this section. Have a great day. Bye-bye.